Okay, so we're now going to talk about what we call the motor effect. So this is a really exciting principle, and this literally changed society, okay? We've got motors because of this effect. So, what is it? Well, when a current is in a magnetic field, it will experience a force, okay? We know from the right-hand screwdriver rule, okay, that current produces a magnetic field around it, okay, from these diagrams. Now, those magnetic field lines will interact with the magnetic field lines from, just bar magnets around it. And when that occurs, they will actually experience a force. So, as I mentioned earlier, okay, if two opposing magnetic field lines interact, they will just cancel. However, if we get two magnetic field lines going in the same direction, well, they can actually produce a force. Okay, so that magnetic field actually becomes stronger, and essentially it can actually cause a wire to actually move, okay, in a certain direction. So this is called the motor effect, as I said, and it happens because the magnetic fields of the magnet and the current interact. Okay, so just have to remember that principle. Now, the direction in which this movement takes place can be determined by Fleming's left-hand rule. So you need to obviously use your left hand, and your thumb is the direction of the motion of the force on the wire. Okay, your first finger represents the direction of the magnetic field. Okay, F, first finger, magnetic field, and your second finger represents the direction of the current. Okay, so second finger, that's current. Okay, so thumb for motion of the wire. Okay, due to the force that it experiences. And basically, in terms of exam questions, they might give you the current's direction, and they could use this notation here. So if it's a dot, okay, that means it's coming out of the page. If it's a cross, that means it's going into the page. Okay, so that means in this case, the current, your second finger would have to point into the page, or the screen in this case, and here your second finger would have to point out of the screen. And then obviously your magnetic field has got to be in the direction of your first finger, okay, and then make sure they're all 90 degrees to each other, and then your thumb will determine the direction that the wire moves in, okay? So, the exam question could give you any two, and you would have to determine the third one, okay? So, how do we reverse the direction of the force? Well, we can do one of two things. We can either reverse the magnetic poles, okay, so reverse the magnetic field, or we can reverse the current. Now, there's another equation which you don't need to remember. This will be given to you in your exam, but, well, essentially it's force equals Bill, okay? It's a nice way you can remember that. But what this equation tells us, it tells us how to measure the magnitude, okay, to actually find the magnitude of the force that gets generated when that current is in a magnetic field. Okay, so that force is dependent on the magnetic flux density, which is essentially the strength of the magnetic field. Its units is Tesla, okay, or capital T, multiplied by current, which units is amperes or amps, capital A, times the length of the wire. Okay, so it's only the length of the wire that is present in that magnetic field. Okay, so length of the wire measured in meters. And again, literally substituting those values into that equation. And again, they could ask you to find out one of those four values, and they would give you three in the question. So just make sure you're comfortable with rearranging this equation. So we could increase the size of the force by making the following changes. We can use a stronger magnet, which will have a stronger magnetic field. We can have a higher current, or we can just have more coils of the wire present in the magnetic field. Okay, so literally it's the length of the wire present in the magnetic field. So I've been going on about this motor effect. Let's see it in action. Okay, or let me explain this diagram for you. So remember I said in an earlier video that the longer end of the battery or cell is the positive end, and here we're using conventional current, so let's follow this arrow around. So we're having positive current going from the positive end of the battery right the way through to the negative end. So let's follow it through. Okay, so it's going up here. Now let's use Fleming's left-hand rule. So we've got current, so get your second finger and point it into the screen. Then rotate your first finger around, okay, with your middle finger or second finger still pointing the screen, okay, and then make sure it's pointing left to right, that's north to south, and then your thumb should be pointing downwards, okay, so that means the force that this section of the wire experiences will be downwards, okay. Let's follow this current around, okay, so it's this time, now our current is coming out of the screen, okay. Now bear in mind this is a 2D image, but this arrow is representing the outward direction with respect to the magnetic field lines which are going from left to right, okay. So with your left hand, have your middle finger pointing towards you or out of the screen, then have your first finger going from left to right, north to south, and then your thumb should be pointing upwards, okay? Now, if we add these two forces together, we've got this side of the wire going upwards, we've got this side of the wire going downwards. If that happens simultaneously, we're going to get a clockwise motion, clockwise rotation, okay? And this is the rotational movement found in electric motors, okay? So that's really, really nice what we've produced here, okay? So we've got electricity, okay, or current producing a magnetic field around it, which magnetic field lines interact with the magnetic field lines from the bar magnet, okay, which will produce a force upwards or downwards depending on the direction of the current, and we get this overall rotational movement, okay. So that is pretty cool. Okay, so just lastly, let's practice using our left-hand rule for this bottom diagram here. So we've got our first finger, okay, using our left hand, going from the left-hand side to the right-hand side, that's north to south, and then let's do side A. Our current is going into the screen, so you need to move your second finger into the screen, so pointing away from you with your first finger still pointing from left to right, which means your thumb will point downwards, okay? So side A will feel a force downwards. This should say side C. Let's do side C. So this time we've still got our first finger pointing left to right. Let's now rotate our finger so that our second finger or middle finger is pointing towards us, away from the screen. Our thumb should be pointing upwards. Okay, so side C will feel a force upwards. Why doesn't side B feel a force? Well, remember Fleming's left-hand rule requires all your fingers to be 90 degrees to each other. Side B has the current going parallel to the direction of the magnetic field, so that's why you don't get a force being produced there, okay? Okay, so what will happen when the left-hand side of the coil reaches the top? Well, I'm going to look at this bottom diagram here. Now, notice the terminals of the battery has changed, okay, or in this case we're using a power supply. Doesn't matter, but what I want you to focus on is this section here, okay? So here the commutator rings, okay, so this is a split ring commutator. Literally there's a gap, okay, if you can see, okay, that's why it's called a split ring, and that gap is there for a reason, okay? It is to ensure that we will get no short circuit occurring, okay? So when current goes up from this terminal, okay, through this side of the ring, if there was if that gap wasn't present, the current would literally just go directly across and into this section of the wire and go to this terminal, okay, and literally would bypass this coil, this section of the coil of wire, okay. So this gap here is quite important, but it also means for a split second, and when this, as the question states, when the left hand side of the coil reaches the top, so here's the left hand side, when this rotates and it's all the way up here, okay, that's when these gaps are going to be, well, they're going to be either side of these connectors, which means there's going to be no current in this coil of wire for a split second, okay, when it's vertically upwards like this, okay, or when it's parallel to these permanent magnets. But that is not important because the momentum of that movement, okay, that's caused the left hand side to move upwards and the right hand side to move downwards, will carry it to the other side, which means the other side of the split ring will connect up to the connector here, and the other side will connect up to this connector here, and therefore we're going to get current flowing again, and then we get the motor effect, or we get the force, the respective forces being produced. Okay, so that's why we are going to get no we're going to get no additional force for a split second, but the momentum of the previous force is going to carry it through. Okay. Okay, and finally, how could the motor be made to spin faster? Well, we can do one of three things. We can increase the current, which means increasing the voltage of our power supply. So we're raising it from 2 volts, let's say, I don't know, to 10 volts. Okay, or increasing the size of the magnet, which means we're going to generate a larger magnetic field. And then finally, we can increase the number of coils that the wire has inside that magnetic field. Okay, so that's the end of P12.